Imagine you are on a call while riding a train. Your phone is mid download when the signal from the first cell tower fades and a second tower grows stronger. A packet of your data is already in flight toward the old tower. If the phone switches towers right now, where does that packet go? Does the download stall? Does the call drop? That tension is the whole problem of mobility in cellular networks. The device must change which tower serves it, but the session, the conversation between your phone and the internet, has to keep flowing as if nothing moved. In LTE, one elegant answer is called an X2 handover. It is a carefully staged handoff between neighboring base stations that keeps packets moving the entire time. No magic, just a temporary bridge, then a permanent route change. Over the next few minutes, we will watch that story unfold stage by stage. Before the move, preparation, execution, completion, and the quiet after. By the end, you should be able to see for yourself how a phone can change towers without dropping the delivery. Before any tower changes, we need the cast of characters. Think of the cellular network as a delivery system with four kinds of actors. At the bottom sits the UE, the user equipment. That is simply your phone or modem. It is the customer waiting for packages. Next come the E-Node Bs or eNBs. These are the cell towers, the local depots that talk to the phone over the radio. In a handover, we care about two of them, the source eNB, which currently serves the phone, and the target eNB, the neighboring depot the phone is about to move toward. Above the towers lives the core network. Two names matter here. The MME is the mobility management entity, the control plane brain that tracks which tower serves which phone and handles signaling. The SAE gateway, or SAEGW, is the data plane hub. User traffic to the internet passes through it. Here's the part that matters for intuition. Radio links are local and changeable. Core routes are more official and change more carefully. An X2 handover exploits exactly that split. Move the radio quickly between neighboring towers, then tell the core afterward. You should now be able to picture four roles: phone, two neighboring towers, a signaling brain, and a data gateway. Everything that follows is about how paths among them rearrange. Stage 1, before handover. The phone is happily attached to the source eNB. Over the air, it has a data radio bearer. Think of that as the last mile wireless lane carrying user packets up and down. From the source eNB up into the core, an S1 bearer runs as a GTP tunnel toward the SAE gateway. That is the official highway for user data. Separately, S1 signaling ties the source eNB to the MME so the network knows this phone is here. The target eNB is already on the map as a neighbor, but it is not serving this phone yet. That is a common misconception. Seeing two towers drawn side by side does not mean both are active for the same device. Only the source owns the radio connection and the live S1 path. Uplink traffic rides from the phone up through the source and into the gateway. Downlink traffic comes the other way. Gateway, source, then over the air to the phone. Clean, simple, one serving tower. Plain language, the phone has one current radio connection, even though a second tower is already nearby. The network has not prepared a move. It is simply serving. That resting state is what we are about to disturb, carefully. Why involve a special interface called X2 at all? Neighboring eNode Bs can talk to each other directly over the X2 interface, without bouncing every coordination message through the core. That matters for speed and for continuity. If every handover had to ask the MME before the phone could leave the old tower, the radio gap would stretch. With X2, the source and target can prepare a move between themselves, then only involve the core when the new serving tower is already holding the phone. Picture two neighboring depots that share a private road. Packages can be handed across that road temporarily, while the main highway from headquarters is still pointed at the old depot. Later, headquarters updates its maps. That private road is X2. X2 carries two kinds of things we will watch carefully. X2 signaling, dashed green in the source diagram, is the conversation that sets up and tears down the handover. An X2 bearer, a solid red GTP tunnel, is a temporary data pipe used for direct packet forwarding between the towers. So the design idea is make before break at the radio edge. Build the neighbor relationship and the interim pipe first, move the phone, then fix the core route. Next, we watch preparation begin. Stage 2, handover preparation. The source eNB decides a handover is needed, typically because measurement reports from the phone show the target cell is becoming stronger. Preparation starts while the phone is still fully attached to the source. The phone does not jump yet. Over X2 signaling, the source asks the target to reserve resources for this phone. The target checks admission, prepares radio configuration, and answers back. If all goes well, both sides now share a plan: which radio parameters the phone will use and how data will be handled during the move. At this moment, the official S1 bearer from the core still points at the source eNB. Nothing in the MME or gateway has changed. Preparation is edge local. That is deliberate. We do not want the core thrashing on every possible move. A critical product of preparation is readiness for direct packet forwarding. The target is now willing to accept downlink packets that the source may forward over an X2 bearer. Think of labeling a side door at the new depot so couriers from the old depot can drop packages there. Pause on the misconception. Preparation is not the handover itself. The phone has not detached. The serving tower is still the source. What changed is that the destination is ready, and a temporary bridge can open the moment execution starts. You should now see the handover is prepared first. The phone does not have to move before the next tower is ready. Zoom in on direct packet forwarding, the heart of seamless X2 mobility. While the phone is switching its radio, downlink packets may still be arriving at the source eNB from the SAE gateway along the old S1 bearer. If those packets had nowhere to go, they would be lost the instant the phone leaves the source. So the source forwards them across the X2 bearer to the target eNB. The target buffers or delivers them once the phone attaches. Uplink is usually simpler after the phone camps on the target. New uplink can go target to core, while any residual pieces are coordinated in the procedure. In the source diagram, this shows up as a red X2 bearer tunnel between the two E-node Bs, with downlink arrows still flowing. The green data radio bearer will soon reappear on the target side. The brown S1 bearer still feeds the source until the later path switch. Here is the plain language payoff. Forwarding is a temporary detour, not the final design. It exists so in-flight downlink is not stranded at the old tower, like rerouting a delivery truck through a side street while the main address is being updated. Anticipate a misconception. Forwarding does not mean the core already knows about the target. The gateway may still be sending to the source. The source is covering for that lag by pushing packets sideways to the target. The core will learn the truth only in the completion stage. Stage 3, handover execution. Now the phone actually moves. The source commands the phone to hand over to the target cell, using the configuration prepared earlier. The phone detaches from the source eNB, the old data radio bearer comes down, and begins accessing the target eNB. It synchronizes, sends a handover confirm, and a new data radio bearer rises on the target side. During this window, downlink packets that land at the source continue across the X2 forwarding path so the target can deliver them after the phone arrives. From the user's point of view, the gap is meant to be short, a brief radio interruption, not a session teardown. Notice what has not happened yet. The S1 bearer from the SAE gateway may still terminate at the source eNB. The MME still considers the source the serving node until path switch. Execution changes the radio attachment first. It does not instantly rewrite every core tunnel. That ordering is the insight students often miss. Handover sounds like one atomic flip. In X2, it is sequenced. Prepare at the edge, move the radio, keep forwarding, then tell the core. Each step removes one risk: unready target, lost downlink, or stale routing, before the next begins. Plain language, the phone can change its serving tower because packets have a temporary route across the two towers. Let us separate uplink and downlink during execution because they do not behave identically. Downlink is the fragile direction for in-flight data. Packets are already in the network, heading toward whichever tunnel the gateway still uses, often still the source. Direct packet forwarding exists primarily so those downlink packets can slide from source to target over X2 and reach the phone after it reattaches. In the legend, downlink is the red downward arrow. Uplink is generated at the phone. Once the phone has a working data radio bearer on the target, new uplink can leave via the target. The upward green arrow in the diagram marks that user traffic climbing from the device. There is less need to chase uplink back to the old tower because the sender has moved with the radio. Bearers versus traffic arrows matter here. A bearer is the pipe, data radio bearer over the air. S1 bearer as a GTP tunnel to the gateway. X2 bearer as the temporary tunnel between towers. Traffic arrows are the packets actually moving on those pipes. Signaling paths, purple, orange, and green dashes in the legend, are the control messages that build and tear the pipes. They are not user data. If you hold one picture, downlink may still enter through the old official door and take the side bridge. Uplink starts using the new door as soon as the phone can open it. That asymmetry is why forwarding is drawn so prominently on the downlink side of the story. Stage 4, Handover Completion. The phone is on the target eNB. Forwarding has protected downlink. Now the network must make the new reality official. The target eNB triggers a path switch procedure toward the MME. In plain terms, the target says, "This phone is with me now. Please switch the user plane path so the SAE gateway sends traffic here, not to the old source." The MME coordinates with the gateway. The S1 bearer is updated to terminate at the target. Signaling relationships realign so control and data both agree on the new serving eNB. Watch the diagram morph. The brown S1 bearer that used to feed the source swings over to the target. Downlink no longer needs the sideways X2 detour because the main highway already points at the correct depot. This is also when leftover forwarding can drain and stop. The temporary bridge has done its job. Completion is the moment the edge local move becomes a core network fact. Misconception to kill. Path switch is not another radio handover. The phone already moved in execution. Path switch is paperwork and routing, essential paperwork, because without it, the gateway would keep shipping packages to a tower the phone has left. Plain language, the temporary bridge carried us through the move. Path switching makes the new route permanent. Still inside completion, one cleanup step remains. Release X2 resources that existed only for this handover. The X2 bearer used for direct packet forwarding is torn down once path switch has landed and buffered packets are delivered. X2 signaling completes the transaction between source and target, confirming success, releasing context at the source, and freeing radio and tunnel resources that no longer apply to this phone. Why not keep the forwarding tunnel forever? Because it was a patch for inconsistency between radio reality and core routing. After path switch, that inconsistency is gone. Keeping extra tunnels would waste capacity and complicate failure handling. Clean design removes the scaffold after the building stands. In the source diagram, completion shows both the path switch with the MME and the release of the X2 arrangement. Order matters pedagogically. Switch the official path first so traffic is safe, then dismantle the temporary path. Make before break ends with break only when safe. After release, the source eNB is no longer in the data path for this phone. It returns to being just a neighbor, ready, perhaps, to become the target of some future move in the other direction.